Okay, so this is gonna be a video that I can combine with the etching stuff I was fiddling around with. But at forehand I want to say everything I do, and this is usually the case by the way, is something I do for the first time. Maybe I did something similar, but usually it is a new idea, because I'm not gonna redo ideas that I already did that worked or did not work. Especially did not work. I'm not gonna redo stuff that didn't work unless you change something. So yeah, it might be a complete fail, but there is quite often people asking about Rubanoids, and I mentioned it that I wanted to do a Rubanoid again because it's been a while and I never built two, and it's quite hard to judge something if you only have one. You know, normal a mono speaker sounds quite boring. So I'm gonna make two this time. I'm gonna make it simple and not super extraordinary like huge big fucking magnets. But there's another thing that's quite interesting, because I had the same problem. Femm. It's nice to be able to model your magnet motor, but to start with Femm is quite a crappy job. I didn't understand nothing of it actually, and I'm still an insane noob in Femm. But I'll show you what I do know, or I hope it's correct, but what I use to see what changes you make in the motor, magnet motor design, and what it results in Femm. So you have a clue if it's worth to whatever, you know, get bigger magnets or maybe use a smaller gap, etc. So I'm only doing the magnetics, not the coil, in Femm at least. So, Femm it is. Well, you can download it for free. Don't know where, probably something with Femm in the name. Google it, you will find it. I opened a new document and you choose magnetics problem. It's not a problem actually, but okay, magnetics problem. Then first we go to, let me see, properties and then material library. We had to add some materials we're gonna use. Most importantly is air. We are gonna use air. So I'll just slide it into the other window. Then PM materials are the magnets and such. In this case I think my magnets were Neos, that's for sure. I'm gonna use really tiny Neos, by the way, something you can buy for 70 cents or something a piece. I think they were 37, might be 40, but we go for 37. Then we're gonna use some steel. Oh no, it's low carbon steel. And I picked, what did I pick? I go with the middle. But you can dive into that and look the properties of a certain steel up. But I'm not getting to the insane saturation points of different kinds of steel, so it shouldn't be a problem. Whatever kind of steel you grab. Some steels you can get a little bit more oomph out, but I just use cold rolled steel. This is one of the bars I'm gonna use. It's a used bar for a few projects, so I have to clean it up, but I got several of those. So I'm gonna use these. This is cold rolled steel, very simple. But it's a little bit better than the normal steel. Cold rolled steel is dimensions are more accurate and doesn't have like this scaling crap all over the place. So okay, we got air, we got the magnet, we got steel. That's what we need. Then you got a grid here. It's very tiny. You probably can't see it. And we're put it on. Let's say 10 millimeter for now. And we're gonna zoom out. There's probably a shortcut, but I don't know which one it is, so I'm gonna just no clue what it is. So I just use the buttons. So we now see points, and this is our grid of 10 millimeters a point. We're gonna put some dots here randomly on the screen. So you have to really select the dot. Then we're gonna connect them with the wire thingy. It's beside the dot icon. We create a region. Not a very accurate region, but that's okay. Because we have to say, within this thing we're gonna model our thing. But every closed object has to have a property. So in this case, and this green kind of dot thing is the material tool or something. Just dump it in here, and it says none. It's not having a material declared. When you select it, you can select it with the right mouse button, and if you press spacebar or space, you get the properties of this point. We're gonna say this is air, and press OK. So now we're going to change the grid size to 1 millimeter, and we're going to zoom in quite a lot. Okay, we're zoomed in. I'm going to use this metal steel. You can model with your own metal. This is 20 millimeters wide and 8 millimeters thick. So what we're going to do, you draw with these stupid dots. Usually I just count them. So 1, 2, 3, 4. Oh, that's another thing. We want to have snap to grid on. It's above the grid size icon, because otherwise you're just making points everywhere. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 millimeters wide, and 1, 2, 3, 4, 5, 6, 7, 8 millimeters thick. So we got our 4 points. Now we're gonna connect them with this wiring tool again. It looks like this program is made in 1990 or something, I don't know. So we got this block, and we're gonna declare it as well. So we get this material icon again, this green thing that says none. We're gonna select it with the right mouse button, press space, and we're gonna say this is steel. This thing is steel. Now we're gonna draw the magnets, and they're 1 millimeter thick in this case, 20 millimeters wide, and 40 millimeters long. But we're looking from the top, so we're looking like this. So what we see, if the magnet is here, is 1 millimeter thick. We're gonna connect the dots. So now we have one magnet here. I didn't declare it yet, but I'm gonna use 2 of them on top of each other. So 2 magnets. Then I'm gonna use the copy tool, but that's usually you have to think a lot to use it. It's also quite crappy made. So I'll get the select tool, this thing here. Make sure you have the wire thing selected, because otherwise it only copies the dots. We're gonna select this block, going to edit, and then we want to say copy, and then you have to fill in how much it has to shift and copy it. So at least it's one time the thing itself, so that's 8, plus these two magnets, so it's 10. And it's in this direction, so it's minus vertical, minus 10. Now hopefully I do this correct, because usually I don't. And this time I did, so that's nice. And now we're gonna copy this whole thing to this side. And then we have our complete motor. Edit, copy. Now we have to find out how much it has to shift. Well, at least 20 and then some. So vertical shift in this, horizontal shift, sorry, is 20, and the gap, well, let's start out with a moderate 4mm gap. So we move it 24 millimeters. 1, 2, 3, 4, 5, 6. That's weird. Let's see if I made the the steel wide enough. Let's zoom in a little bit. This is the reason why I usually place dots all over the place. 1, 2, 3, 4, 5, 6, 7. Yes. So I made it all too small, as usual, but we'll fix it. Up, up, up. You have to remove these pieces in between, otherwise it will flip. We're gonna do this here as well. So, is this correct? This has to go, this has to go. So we're back on track. We got a gap here of 4mm. This is where the coil is gonna sit, and it's a top view, remember. So actually I can show you sort of. So we're looking on top of the Rubanoide. This is the magnets that I drew in Femm. Now I only gave this a material, this block here. It says steel, so we have to do it for the rest as well. This is also steel, this is also steel, and this is also steel. Then we want to declare the magnets. And the thing is, the grid size is 1mm, so wherever I click I won't be able to put something in this magnet. So you have to change the grid size to 0.5, so I'm able to put something here. Then I select the magnet, neodymium, and then we have to fill in the magnetization direction, and in this case it's axial. So if this is 1mm, it's magnetized like this. I push. So we choose 90. Oh, well, it's the opposite, it's the other way around. It's pointing upwards, but it doesn't really matter. We're gonna do this with this magnet as well. Choose its magnet, and then say 90 degrees. Now on the other side, here, we have to declare as well that it's a magnet, same magnet, but the direction of the magnetization, Jesus, hard word. It's not 90, but it's 90 plus 180, because it has to be the other way around, so it's 270. Oh, no, I selected both, that's a problem, so I have to pick something else and go back to the material thing. Select it with the right mouse again, press space. Magnet at 270 degrees. Bang. So we declared all our stuff, so that's a good begin. Now we want to have the middle, actually the middle of this gap So I'm gonna change the grid size to 1 millimeters again. Because we want to know how much magnetic field is here. And what we're gonna do, we're gonna grab the point tool thing, the dots, and I'm gonna put a dot 2 millimeter in front of the magnets and 2 millimeter on the back of the magnets, and both exactly in the middle of the magnetic gap, or the gap. So that's the first part. Now you go to Analyze or Analysis and then choose Analyze, and then we got a fault. Apparently I have to save it first. So save as Rubanoide video. Oh, that was rather quick. Then you go back to Analysis, View Results. We can zoom in again with the annoying zoom thing. You can scroll around with the arrows on your keyboard. So we see something, but not, well, it's not very useful. There's this colorful thing here, and then we choose Show Density Plot. Bang. Then we can at least see something happening in terms of where there is much magnetic field and where it's not. This is usually the picture you see when people post stuff from Femm. So now you know how. Now what we're gonna do, we're gonna measure this between these points we put there earlier. And the thing is, you have to put them there already in the previous window. So that's why I did it there, but usually you will end up here and then like, how does it work? And the whole program is full of how does it work. Besides the dots, there's again a sort of line tool, but this time it's red. We select it and we connect these dots. We want to measure in between here. Then we go to this XY thing and we choose plot type, we choose normal flux density. Number of points in plot, well, let's make it 500 for instance, I don't know. Okay. And this is what we get. You can see the field is a little bit above 4 Tesla, and you can see when it goes to the middle it goes to 0, through 0, and then back the other way around. It's because these magnets were turned 180 degrees. But that's how they should be, because the coil is running up and down, and it's the left hand rule, by the way. I used the right hand rule in one of the videos, or in several videos, but I did explain it right, just the wrong hand, but the result is the same. Left hand rule. If the current moves upwards, for instance, then the magnetic field is in this way. But on the other side of the coil, the current moves down, so the magnetic field has to be in the other direction to have the same movement of the coil. Otherwise it would be pulling or pushing to each other, which is not going to result in any sound. So, a little bit above 0.4 Tesla, not bad. So, and now we can tweak. You can leave this open. And we go back to the drawing, for instance, and select this whole thing. Be sure to have this wire tool selected again. And then I'm gonna move it a little bit. I'm gonna move it. I want to have a gap of 3.5 millimeters, so I'm gonna move it 0.25 millimeters, but horizontal, but minus, so it goes to the left. Otherwise it moves the other direction. And I want this thing as well to move, but in the other direction, so just 0.25. Then we go back to analysis. I must think of a new word for that because I cannot pronounce it. And then view results. We're gonna select this thing again and look for the normal flux density. And now we can compare it. It's like a little bit more than 4.5 compared to around 4. So that's what we gain in just a 0.5 millimeter. That's quite nice. Now you could make this, for instance, 2 millimeters, this gap, and it will be way higher. But the only thing is, if the coil is this length, well, it's gonna be smaller, of course. But if it's like 24 centimeters, it's quite hard to get it so flat it will fit in this 2 millimeters gap without touching. So that's a problem. And another problem is that although this is 8 millimeter metal, 20 millimeters wide, and there are gonna be 2 of these bars on each side, as seen, it's still quite likely if you make a gap of 1 millimeter or 2 millimeter, the stuff bends like this and snaps together, and it's pretty hard to get separated, and your membrane or your coil will be fucked when you want to get them off. So that's a very quick and dirty how to Femm thing. But I think this is sort of the basic stuff. If you know this, you can model all kinds of weird stuff. You can model a ribbon, you can model, you can play with different kinds of materials. Like for instance, if this runs into a point, then the magnetic field here will be really strong. So you collect all this magnetic field and kind of beam it to this small area. You can do loads of fun shit, as well as the planars and such. And you don't actually need to know the exact magnetic field strength of the magnets you got. If you're close or in the neighborhood, it's okay. You can see at least what's happening. So it's not really sure I got 4.5 Tesla. Although in this case the magnets are, I think, this rating, so it's gonna be really close. But sometimes I model stuff while I don't even know the strength of the magnet, but just to see what happens if you change something or make the gap bigger or smaller, or move the membrane further from the magnet, etc. So, quick Femm guide. I hope you will enjoy, or at least can do something with it. I'm gonna draw in SketchUp some more Rubanoide stuff and decide on how much turns I want on the coil, etc. and what kind of material I'm gonna use to make the coil. And then I have to figure out where I put it on, but that's a third video, I think.